Back in 2015, when I was still a young computer science student, I started to work at Intel and rapidly jumped into the world of Lint and compilation. I joined the team that developed a Lint tool for hardware design. In the beginning, everything was new to me. Lint, which at first sight looked innocent or even marginal, appeared to be a powerful, fascinating tool, interesting to develop and with major impact. My name is Maayan Shoval and I'm a software engineer. Today I would like to give you a glimpse into the world of Lint as I find it. We will talk about what is Lint, how does it work behind the scenes, and how it is applicable in software and in hardware. Lint. It is the general name for software that aims to analyze and verify code correctness statically. Means by looking at the code only and without actually need to run it. It is usually follows a bunch of rules, determines what is considered to be a good structure of a code. The term lint was derived from the name of the tiny bits of fiber and fluff shed by clothing, in resemblance to those tiny little defects that sometimes get all over our clothes. In code, little mistakes, stylistic inconsistencies, or even dangerous logic are things to get rid of. This purpose can be achieved using a lint tool. The term lint originates from a Unix utility that examined C language source code in 1978. So we discovered what lint basically is. Let's see how does it actually works. There are two main parts of Lint tool. First are the rules, which are dedicated to check and analyze a range of requirements. And second is the compilation process. Lint is based on a compiler, and so during different phases of the compilation process, different aspects of the program are being analyzed. There are linters for both compiled and interpreted languages, and today we will focus on the compiled ones. Let's have a short reminder on what is a compiler. Compilation is the process of taking code written in language A and convert it into target language B. A known usage is converting a code written in some programming language into a machine-level language in order to create an executable file. Another usage is compiling a code that describes hardware design and translate it into the target of hardware physical model. We will go over some of the phases of a compiler on high level to see what information the linter can conclude and analyze at each phase of the compilation. First phase is lexical analysis. In this phase, the compiler reads the sequence of characters in the program as tokens and converts them into meaningful lexemes. This is the basic phase of the compilation process, where the compiler scans the code. Here, the character stream is grouped into meaningful sequences called tokens, and entries of the corresponding units are being created in the symbol table. Second phase is syntax analysis. In this phase, a syntax tree is being created, checking if a given input is in the correct syntax of the programming language or not. This phase is all about figuring the structures in the code. Here, the compiler determines whether or not the text follows the expected format of a specific programming language by constructing a parse tree with the help of tokens from the previous phase. The linter can then use information gathered by the compiler so far in order to collect and identify issues about all in regards to correct structures of the language. For example, unbalanced parentheses or missing semicolon. Third phase is semantical analysis, checking whether the parse tree constructed follow the rules of the language. Here, the consistency of the code is being checked. Using the syntax tree from the previous phase, along with the symbol table, the compiler verifies that the given source code is semantically consistent. It will check, for example, for type mismatch and incompatible operands. The linter can then use this information to alert about issues in regards to semantics of the program and about issues derived from the syntax tree, such as incompatible value assignment, infinite loop, or even unreachable code. We focused on some of the phases of a compiler and discovered how can a linter benefits from them in order to analyze code. Let's see how lint is being used in software programming. A linter is commonly used as an internal tool of an IDE, based on the requirements of the programming language that is being used. When using an IDE, you probably have encountered the capability of underlying issues in the code as you type. This is the result of a linter running in the background of your IDE, allowing highlighting, underlining, or identifying problem areas in the code before running it. Another usage of a linter is as a standalone software that is based on custom-made requirements rules, which depends on the specific project definitions. The linter then follows the compiler API to identify issues during the compilation phases, same phases as we talked earlier. Let's have a small example. For the example, I will use C++ programming language, but this can be done in any other programming language. Say we are currently developing a game, and we have a building block of a figure class. We want our software to be in good practice for this project, so we decide to have a requirement of each figure object must start with the letter F. So we want to get an error if this is typed, and we want this to be the correct syntax. Say we are using a lint tool for the project, and we want our lint tool to handle this requirement. We remember that lint is basically enforcing rules. So first, we need to have a matching rule for the above requirement. In order to write such a rule, let's see what information we need. We need to know if an object was created and of which type. The question is whether we have this information and when. So when do we actually have the information about the type of an object? To answer this question, let's remember what are the compilation phases the linter is based on and what it can achieve in every phase. In the lexical part, the compiler reads the characters and gathers them into tokens, and then illegal tokens are being recognized. In the syntactical part, composing a parse tree, figuring the structures of the code, then broken structures are revealed. And in the semantical part, the compiler checks if the code conveys an appropriate meaning. In this phase, we saw an example of type checking. While having this in mind, can you tell after which phase the compiler will have the needed information for our rule? The information about the object's statically typed creation? This will be after the semantical analysis phase. Well done to all of you who got it right. So, we figured out when the compiler will have all the necessary information about the objects in the program. Now let's draw an outline of our rule in pseudocode. First, we need to fetch all objects of type figure. And to do that, we'll base on the information from the compiler. Remember, this information is available after semantical analysis phase. Then, for each figure object, we'll check whether or not it starts with an F. If it is not, we'll flag a violation of this rule. So, in conclusion, we got a requirement that is based statically on the code, and we used lint mechanism to achieve it. So far, we talked about how lint is used in software programming. Let's see how does it work for hardware design. Like software programming languages, there are several languages of hardware description that are used to create a hardware design. This group of languages is called RTL, Register Transfer Level, which includes, for example, System Verilog and VHDL languages. In resemblance to software programming languages, also hardware description languages are being compiled. This time, instead of creating a binary code, the compilation process will create a hardware modeling made of gates and wires. In analogy to what we saw in regards to software programming, in hardware design, there is also the need to verify the code. Lint has become the generic term given to design verification tools that perform static analysis, based on a series of rules and guidelines which reflect good coding practice. In hardware, Lint can be even more powerful than in software, recognizing input-output mismatch, race conditions, incorrect usage of blocking and non-blocking assignments, set and reset conflicts, or even deadlock conditions. In RTL, the building blocks are modules, which includes port, data type, functionality, and timing. In software source code, we saw earlier an example about issues of the syntax itself. We wanted to force a requirement on the code syntactically. In hardware design, by only reading the code, along with the given constraints of the project, such as timing and area, we can actually conclude a lot about the design. Let's take, for example, a design which is built of two modules. Each one is connected to the other. The linter can detect, for example, issues of input-output mismatch between the modules. And when talking about circular dependency, we can think of some issues that might arise. A linter can take into consideration clock resolution and can detect race or even deadlock conditions. Different rules can be categorized into different severities, depends on their importance. So, when having a violation of some rule, the user can decide whether to alert it immediately or if it can wait. For example, when talking about syntax rule that checks indentation of the code, it will probably be in low severity. And for example, rule which is checking for suspicious structures in the code that might cause a critical bug will be categorized as high or even showstopper severity. Another aspect for Lint in hardware design is the fact that it can detect and prevent bugs before simulation of the hardware. So as a result, it reduces the time of the overall production process. And when talking about hardware for autonomous vehicles or medical products, getting the ultimate coverage of all edge cases can actually save lives. To wrap it all up, we talked about Lint, a static analysis software, which is based on the phases of a compiler, and we focused on some of these phases. We saw how Lint can be dedicated for the analysis of program written in multiple programming languages, both for software and for hardware. And now that we all understand the strengths and the capabilities of Lint for various use cases, we can all go back to our favorite IDE, confidently use it, knowing what's going on behind the scenes. Thank you all for listening, and feel free to contact me on LinkedIn.